Okay. So, yes, so this is the last lecture, and we stopped yesterday after the derivation of the scalar two-point function. So we talked about these adiabatic perturbations. We defined this parameter, this variable field zeta, that is directly capturing the adiabatic perturbation, and we related zeta to fluctuations of the inflaton field here. And then we use our result for the inflaton two-point function to get the power spectrum for zeta. Now, as I mentioned yesterday, one can derive this result in various ways. One nice place that one can see the derivation in a concise and relatively simple or maybe more straightforward way is a paper by Maldacena called Non-Gaussian features of non-Gaussian features of, I think, single feed inflation, something like that. Very famous paper, so you'll find it. It's also mentioned in my lecture notes. Oh, maybe I should also say that you have probably seen there are my lecture notes. There is a link in the program, and there are more materials. So many things that I didn't have time to talk about here, you can find there. And of course, most of them are coming from other references. So I have some references there. So if you are interested, feel free to take a look. And also, if you have questions about the subject, you can always email me. All right, so to continue, so we talked about scalar perturbations. Now, as I mentioned also yesterday, this system that we are studying is in inflaton, and it is coupled to gravity. If it did not have inflaton, as you have seen, for instance, from lectures by Ricardo, in gravity, we have 2 degrees of freedom, 2 tensor degrees of freedom. Now, when we couple it to inflaton, we are adding one scalar. So this is the scalar. Of course, the 2 tensor degrees of freedom also exist. We can compute the correlation function in a very similar fashion. And if we do that, we will find the following. So there is a little bit of notation that I should introduce. So we decompose the metric perturbations. I'm simplifying things a little bit. I'm just writing the dynamical degrees of freedom that we care about. So we write it as a squared e to the 2 zeta. This zeta was the scalar perturbation in a particular choice of time slices. And then if we want to also include tensor perturbations, there will be changing the tensorial structure of the spatial part of the matrix. So here there will be a gamma ij. And this gamma ij is transverse and traceless. dxi, dxj. So this transverse gamma ij's, if we go to momentum the space, we can expand it in terms of 2 polarization vectors. So then we'll have, we will write gamma ij equals gamma r epsilon r ij, where r can be either 1 or 2. These are the 2 polarizations. And these polarizations are, so this is in momentum space. So this is gamma ij of k, this gamma r of k, and this polarization depends on the direction of the momentum vector. because it has to be transfers to that. And then, of course, it matters how we normalize it if I want to talk about the power spectrum of gamma R. So we normalize this epsilon, this polarization vectors to in the following way. So if I multiply two of them together, I should get delta of R and S. And here, the repeated indices are summed over. So with this normalization, then we can find the power spectrum for these two modes of the tensor perturbations. The computation after this decomposition actually becomes almost identical to the computation for this scalar field. Like every component of gamma is has satisfies the same equations as that of the massless scalar field. And then the final result for the spectrum of tensor modes turns out to be the following. So gamma R, K, gamma S, K prime is equal to H the star the squared is a factor of 2 and Planck the squared K cube times delta of R and S. So the two polarizations are decoupled from each other, and then the usual delta function of momentum conservation that comes from translation of invariance. So now one thing to notice with this result is that if you compare the scalar perturbations, so notice that these are now both of them fluctuations of the metric. Both of them are dimensionless quantities, and they appear in a similar way. Like here, if you expand this if zeta is small, you can expand it, so it will be a diagonal change in the spatial part of the metric. Gamma ij would be a traceless contribution. So they appear next to each other. They have similar effects. So they look as if they seem as if you are expanding or contracting the space, but one of them is symmetric, one of them is like tensor mode. But the amplitudes are different, right? Because here, apart from this order 1 factor, there is a 1 over epsilon sitting here, which is not there. So therefore, the scalar perturbations are bigger than tensor perturbations. Now we can make this we introduce a parameter R tensor to a scalar ratio that captures this difference between the strengths of a scalar and tensor perturbation. So R, use blue. So R, which is tensor to a scalar ratio, is defined as twice P gamma. So P gamma is what is multiplying the delta function of momentum conserving. 2 pi cubed times the delta function. So R tensor to a scalar ratio is defined as twice P gamma divided by P zeta. And this turns out to be 16 epsilon. Why 2? Because there are 2 polarizations of the tensor modes. So this is one important prediction or quantity observable of inflationary models that we have some constraints on tensor to scalar ratio. So of course, as you know, we have not detected these tensor fluctuations. Also, they are called primordial gravitational waves. So these are these gammas. What else? We have observed the scalar perturbations, and we have observed them with enough accuracy or over enough large enough range of scales that we can actually see the k dependence. So as I mentioned yesterday, the k dependence, there is one explicit k dependence here, k cube, and there is an implicit k dependence because this h star and epsilon star are evaluated at the time when the particular k mode is crossing the horizon. So when we say h star, we mean h at the time tk. And when we say epsilon star, we mean epsilon at the time tk. What is tk? Tk is the time when k over tk is equal to h at that time tk. So this is an implicit definition of the time. It's the time when, if you remember these diagrams, it's the time when a particular k mode that we have is crossing the horizon. So therefore, we can compute the tilt deviation from a scale invariance based on the fact that there is this implicit k dependence here. So using this equation, this definition of tk, we can see that what is called ns minus 1, which is defined as d of log k cube p zeta of k by d log k is equal to twice. So this will be related to the slow parameter again, because if the slow if we are in exact de Sitter, nothing changes. So I don't go through the derivation, but it's not too hard to derive this relation between for the tilt of zeta. And now notice that obviously if p zeta goes as 1 over k cube, and s minus 1 would be 0. So that would be exact the scale invariant the spectrum. Similarly, we can also define the scalar tilt. That seems maybe a bit too futuristic to observe, but it's easy to compute, so I can just write it. So in a similar way, we define tensor tilt and tensor tilt is, of course, much easier to compute. It is just minus 2 epsilon. Let me derive the tensor tilt just for you to get an idea of how it works. It's very easy, right? Because essentially what happens is that this derivative with respect to log k, this derivative with respect to log k, since we are multiplying by k cube, it kills this 1 over k cube. So it's really just the time dependence of the overall coefficient. Then if we use this, we can see that up to corrections which are slow roll suppressed, for instance, nt becomes just 1 over h d by dt of log of k cube p gamma of k, which is nothing but 1 over h times d by dt of log of h squared, because the other factors are either constant or the other factors are constant, not time dependent. So and the only thing that remains is h squared, and this is twice h dot divided by h squared. But then you can easily see that h dot over h squared is minus epsilon. So this becomes minus 2 epsilon. Now, why do we have, for instance, this eta, 2 eta minus 6 epsilon here for the scalar? Because there is an extra time dependence coming from this epsilon here. Okay, so there are these three observable, in principle observable. Oh, of course, the first observable would be the amplitude of a scalar fluctuation. This is also something that we have observed. It's something about the 10 to the minus, the variance is something about 10 to the minus 9. We have observed that too. So that would be the first observer. Maybe I should say that's the first observer. And then these are the other three, in principle, observable. Among the three, ns minus 1 has also been observed. The other two have not been. Now, one thing that you can see here is that there is a relation between the tensor tilt and tensor to scalar ratio. This relation is sometimes called tensor consistency condition. So if we manage to measure both of them, then we see that NT is equal to minus R over 8. So it's a relation between two observables. That's why it's called a consistency relation. So this model uniquely predicts this single relation. Okay, any question so far? Yes? Oh, yeah, that's a very good question. So the specific form of the potential is encoded in H, epsilon, and eta. Why? Because, say, for instance, H is the easiest. Depending on how big is the potential, remember that the potential acts very similarly as a vacuum energy, a cosmological constant. It's like a changing cosmological constant. So the value of potential will determine the expansion rate. So therefore, H depends on the value of the potential. Epsilon and eta depend on the derivatives, the first and second derivatives of the potential. So in this way, these observables depend on the potential. In fact, what I'm gonna do now is to consider a particular potential, m squared phi squared, and show you how it gives you specific predictions for these observables and how they are ruled out. Yes? Oh, well, it's just adding up the two polarizations. Because there are two polarizations of the tensor. This is a definition. Of course, you could decide not to define this, but the logic behind it is that the tensor power is coming from the two polarizations. So you add the powers together and then divide it by a scalar power. Upper limit on R. Yes, very good question. It is. This is what I wanted to say next or at some point, but I say now. R experimentally, let's say R experimental is less than 0.03, right? Something like that. 0.05. Okay, 0.05. Other questions? Uh, Higher order corrections to which, to this one? So you are asking if I can find higher order corrections in its plural parameters. Sure, yes, you can find them. Essentially, what we are doing is a perturbation in its plural parameter. So it's as usual. Perturbation theory is something very systematic. You can continue going to higher order, but there is not much point because the plural parameters are a border percent, and we don't have enough precision to see that those corrections. Or maybe I should have said that since it's related to what you are asking. There is this other, of course, this ns minus 1 itself is something that depends on the scale in principle, right? It would be a very particular situation in which ns minus 1 is a constant. Then you would have an exact power law. Generically, you would expect that one to also change. That change of ns minus 1 with the scale is called running. But that would be similar to what you are saying. It's like a higher order correction in its plural parameters. And at the moment, we haven't detected running. So with our predictions, running is something second order in its plural parameters, and so far it is within our error box. Yeah. You can infer reheating temperature if you know, if we measure tensor mode. Why? Because okay, let me say this. So if you measure tensor modes, then you know what is the Hubble scale during inflation. If you know Hubble scale during inflation by Friedman equation, you know energy density. Okay, so now if you assume now, so what will you learn really? You learn the energy density during inflation at the time when the observable modes cross the horizon. So assuming by making some assumptions about what happens during reheating, then yes, you can determine the reheating temperature. For instance, you can say that reheating temperature cannot be larger than something, right? Because you have some energy density here. The best thing it can do is to remain more or less constant. It cannot grow because of the null energy condition. So at best it remains constant, maybe it dilutes a bit. If reheating is not very efficient, it might dilute a lot. So reheating temperature can be much lower than what you would expect by measuring the energy density here, but cannot be much larger, right? So you will find some upper bound on the reheating temperature. Okay. Yes, so now we do m squared phi squared. So I can erase. So just to have an example of how the potential um, can be ruled out or can give prediction for this observer. So before even talking about the um, what would be the predictions for those quantities, first of all, let me just say that the m squared phi squared can give inflation. Of course, in order to have slow roll inflation, we needed some slow roll condition to be satisfied. Now, in pictures, m squared phi squared might look too steep compared to what I drew in the first lecture. So you might wonder how come it can give me inflation. Of course, one should ask it quantitatively. What we really want to achieve is to have a small slow roll parameters. So the slow roll parameters for this potential you can easily compute. Remember, epsilon was m Planck squared v prime squared divided by 2v squared. Just we can plug this in that formula. Also a very simple formula for eta. What we get is that epsilon and eta are equal to each other and equal to 2m Planck squared divided by phi squared. So it turns out that the slow roll parameters are much less than 1 if phi is much bigger than the Planck mass. So epsilon and eta much less than 1 implies phi is much bigger than m Planck. So indeed, we can inflate on m squared phi squared potential as long as we are talking about field excursion which are far from super Planckian. This is called super Planckian ratio. I should say that this is not necessarily something bad. You might be a bit worried that this phi field is super Planckian, but in fact, what you should really care about is that whether we have curvature scales that are super Planckian. As long as curvature is small compared to Planck scale, Einstein's theory of gravity is a very good theory. Corrections to Einstein theory are expected generically to arise when we go to curvature scales that are Planckian. So what is the curvature scale? It is determined related to the Hubble parameter. So h squared, curvature is of order h squared, and that will be, if we are in this slow roll regime, would be just given by m squared phi squared. Well, basically v divided by 3m Planck squared. So this will be m squared phi squared divided by 6 m Planck squared, because my potential is actually m squared phi squared over 2. So obviously now you can see if we want this to be less than m Planck squared, it just implies that we need mass to be sufficiently small, right? So we need m to be much smaller than m Planck squared divided by phi. So it's not necessarily a problem. If phi is super Planckian, it's enough that mass of the field is sufficiently small so that we are talking about sub-Planckian energy density. Okay, so now how far should we go? Remember that we need long enough inflation. Yes? The wavelengths of? Uh-huh. Mm-hmm. So we care about the wavelengths when they are crossing the horizon. Uh-huh. Uh, mm-hmm. Exactly. Uh-huh. Well, eventually, whatever happens in that regime, they stretch to a regime when we know how to deal with them. And then our argument, remember what was our argument? We just said that we don't have enough energy to excite very high energy modes. If there's no mechanism to excite things, then I just put high energy modes in vacuum. So maybe far in the past they were in the super Planckian regime. Maybe I don't know what happens there. Perhaps it's not even a well-defined question, because what does it mean to be super Planckian? Now, say take Minkowski vacuum, right? And then talk about some particular modes in Minkowski vacuum. So you set them to be in the vacuum. The particular modes in Minkowski vacuum are just essentially harmonic oscillators that you set them to be in vacuum. Now go and do a very large boost. Those modes become super Planckian. But doesn't mean anything. They are just in vacuum. Everything is Lorentz invariant, so you can boost. And the notion of super Planckian, once you go to a regime which curvature is irrelevant, is not a well-defined notion, because you are in a Lorentz invariant theory. Mm-hmm. No, because the predictions only rely on the behavioral perturbations when their wavelength is of order of the curvature scale. And that is much bigger than the Planck scale. That's where you don't have any approximate Lorentz symmetry. You can talk about the preferred frame, there is inflaton fit. Then there, but you are, at that moment, you are completely sub-Planckian, so there is no problem in using this effective field theory. Yes. So what was I saying? Yes. Now, yes, I was saying that we need long enough inflation, right? Like about 60 if we want high scale inflation in order to solve the horizon problem. So we can determine what should be the minimum value of this initial value for the field so that we get this 60 inflation. How do we do that? We look at this in E, right? There was a number of efforts that we said if we are on this slow roll attractor, it's given by phi I divided by phi, let's go phi reheating, time integral of h d phi over phi dot. And h and phi dot are both determined in terms of phi. So I can use the slow roll solution to write phi dot as minus v prime over 3h. So this becomes integral phi I to phi reheating 3h squared d phi divided by v prime, and then 3h squared. Again, I can use this slow roll solution to write it as v over m Planck squared. So what I get is 1 over m Planck squared integral from phi I to phi reheating, or maybe phi n v d phi over v prime. If we consider the m squared phi squared model, the answer is phi squared divided by 4 m Planck squared. Phi I squared. Oh, and then there is a contribution from phi n, but that is some order 1 correction, right? Because it ends when phi arrives to the bottom, when phi becomes of order of implied. So the other term coming from the upper bound of the integral would be an order 1 correction. Since NE has to be 60, that order 1 correction I can neglect. And then if I set NE to be 60, then it tells me that phi I has to be of order of 15 M Planck. Okay, now you can also see, just by looking at these two relations, this and this. We can also relate directly epsilon and eta to the number of ephos, right? So this comparison tells us that epsilon in m squared phi squared epsilon is equal to eta equal to what is it? It is 1/2 times 1/2 NE. Is it correct? Yes. All right. So now, now we have everything, right? So this m squared phi squared model becomes very predictive about those 4 quantities. Not 100% predictive in the sense that there is still m squared that I haven't said anything about except putting an upper bound. So how do we fix the value of m? The value of m, we fix it by requiring that, remember that the Hubble parameter, or h squared, depends on the potential. So m will depend, actually here is a good place to look. So if you look at here, you see that Hubble h squared is given by m squared times 4/c, 2/3 m squared times h squared. Times NE. So let me also write that. H squared is given by 2/3 m squared times the number of ephos. The number of ephos is fixed, is about 60. Epsilon and eta are also fixed because the number of ephos are fixed. Now, if we go back to these relations, let's see if I can keep everything. Good. So now you can see now both this, all of the predictions. So as you see, NE, we know what it is. It is 60. So NE is about 60. Yes? Very good question. It is at least 60. However, the observables that we, remember that this NE is measured from the end of inflation, right? Because I integrated from phi I until the end. So there is 60 ephos between this phi I, this point that I call phi I until the end, but phi I, you shouldn't think about it as the beginning of inflation. Phi I is the point when the observable scales are crossing the horizon. Inflation could have started earlier, much earlier, but it wouldn't matter for our observable. So in this plot, whatever happens, inertia. this plot, whatever happened at very early times, it would correspond to the scales that are beyond our horizon, so we wouldn't see. What we see corresponds to 60 if was before the end of inflation. So that's why I put n equals 60. Okay, so now you can see that given that we observe this the scalar power to be 10 to the minus 9 or so, that allows us to fix. So in this equation, the only thing that is not fixed, so epsilon is fixed in terms of NE. H is not fixed because it depends on m squared. So this relation allows us to determine the mass of the inflaton to match with the scalar power. But then ns minus 1 will be exactly fixed. R will be fixed uniquely. And then we can get some numbers. So the numbers that we get is, in this model, we get ns minus 1 equals minus 2 over ne, which is about 0.033. This perfectly matches with the observations. However, unfortunately, for R we get 8 over NE, which is about 0.13, and this is too big. So m squared 5 squared is ruled out by many sigmas. I don't know, 3 sigmas, 4 sigmas. However, there are other potentials. So now as you see different potentials, we give you different values for epsilon and eta, so there will be a potential that works. Now it turns out that since there are constraints on R to be small, it means that epsilon should be relatively small. Right? The problem with m squared 5 squared is that epsilon is too big and therefore R is too big. Epsilon should be small, but tilt is fixed. So if you make epsilon small and keep ns minus 1 fixed, eta has to become negative. So eta positive corresponds to a convex potential. That will be like m squared 5 squared or 5 to the 4th. Those are ruled out. We need concave potentials to match the prediction. Okay, I should also say that the range of R's that, so we have seen R, we have put constraint on R of order of 1% or 5%. It can improve in the near future experiments by 1 order of magnitude. However, the real constraint on the scale of inflation is that this reheating temperature that we have, it cannot be lower than BBN temperature. So there is a very large range of scales between BBN temperature and the scales that we are talking about. So just to give an idea, so this corresponds to sound. So this is the point when we have reheating. So there we know that T reheating has to be bigger than BBN, which is of order of MeV, say 10 MeV. Now we are talking about models that are predicting BBN temperature, reheating temperature that is about the Gauss scale. So T reheating in this m squared 5 squared model turns out to be 10 to the something like 10 to the 15 GeV. So there is a huge range of the scales between what we are constraining now and what could in principle be. Therefore, unfortunately, even though inflation predicts gravitational waves, and that could be a very nice way of adding extra confirmation or ruling out inflation, in practice, it might not happen anytime soon that we rule out inflations, because there is a large range of possibilities that inflation allows. Okay, so now if there is no question, I'll move to non-Gaussianity. Yes? Well, the only thing is what I said, that it has to be larger than BBN, because if it is lower, then BBN wouldn't work as we expect. Maybe there is, that is really the hard bottom. You cannot go below that. Then you might have more theoretical prejudices, like baryogenesis, for instance. We don't have a single known mechanism for baryogenesis. It would probably be a bit hard to accomplish baryogenesis if the temperature of reheating is so low. Perhaps there can be a model, but maybe it's not a very elegant model for baryogenesis. So based on that, you might want it to be high. Oh, maybe I should also say that perhaps gravitational waves, like the stochastic gravitational waves that now we have observed, if they improve by some orders of magnitudes, perhaps that could be another avenue to explore either the gravitational waves that are produced during inflation, or maybe a bit even more promising would be if you have a reheating mechanism that produces gravitational waves. So that is one other way that maybe you can get some handle on this problem. Yes? Uh-huh. Uh-huh. I can repeat it, however, I'm not even sure about the argument anymore, so I can just repeat it, but then it's up to you to go and verify its validity. The argument was that if you take what a nanograph is observing and compute the actual energy density in those gravitational waves, then it's energy in gravitational waves. So if you assume it is primordial, then it will be a contribution to radiation energy density, right? That contribution to radiation energy density, for instance, affects matter radiation equality. And these are the things that BAO peaks in CMB are sensitive to. Like, for instance, that's the way they put constraints on the effective number of relativistic degrees of freedom, like N effective, you might have heard. This would be like a contribution to N effective. And then the argument was that unless this signal at nanographs is stopped abruptly outside the window that they observe, it will be too large and effective. That was the argument. I should say that I don't know if it's true. Okay. Okay, so now non-Gaussianity. So far we only consider perturbations at a linear level. Of course, even if we consider M squared phi squared model in which phi appears quadratically in the action and therefore linear in the equation of motion, still we are dealing with an interacting theory. Why? Because gravity, it is coupled to gravity, and gravity is a nonlinear theory. So there are interactions, and when there are interactions, you will not get a Gaussian correlation functions. Interactions produce connected correlation functions at higher order, which means that you will not be Gaussian. There will be deviations from Gaussianity. So this is another very inevitable prediction of inflation. Maybe it's not even, maybe I shouldn't even call it prediction. It's just an inevitable fact of life that we cannot have just Gaussian perturbations just because we live in a universe where there are interactions, fortunately. But okay, so now we would like to look for those non-Gaussianities. That those non-Gaussianities are actually very useful. Why are they useful? Because, as I mentioned, say with the current observables that I talked about, they are just a couple of numbers, right? You can always find a potential that matches those. Therefore, if you want to get if you want to determine what happened during inflation, you want to find some more intricate observables that are more sensitive to the details of what's going on there, instead of just those couple of numbers. And then non-Gaussianity is essentially probably the most promising avenue to be able to distinguish different models of inflation or see a new signal. Okay, so now let me just give you a simple model, one of the earliest models for non-Gaussianity, which is called local non-Gaussianity. A very simple model, which I think perhaps is useful to illustrate the general idea. So suppose the observable, the adiabatic fluctuations that we observe is related to some Gaussian field in a nonlinear way. So it is given by g of x, where g is Gaussian, times 1/2 FNL local times g squared of x. Why is it called local? Because it is a relation which is local in the space. Like zeta at this point depends on g at this point in a nonlinear way. And g is Gaussian, as I said. Now, in this model, if we go and compute the 3-point function, so now to save time, I'm going to do this. I put a prime here, and this means that I'm not going to write the momentum conserving delta function. So everything that I write it has momenta that sum up to 0. But I'm not going to write that delta function anymore. So if we go and compute this 3-point function in this model, very simple model, we find the following relation. pk1, pk2 plus permutation. Of course, this is connected because there is no disconnected 3-point function. So this is a very simple model. It's a model that people actually use for instance, the Planck data to constrain. Now, it has a particular feature which is very important. And that feature is that if I take the limit in which one of the three momenta is much smaller than the other, and this limit is called the squeeze limit for the following reason. So remember that this K1, K2, K3, they add up to 0, which means that they form a triangle. K1, K2, K3. So now, if I take one of these to be much smaller than the other two, this is called the squeeze triangle. And this local non-Gaussianity has the property that in the squeeze limit, which now I follow Marco and write it like this. Minus q over 2 zeta of q in the limit that q is much less than k. And this local non-Gaussianity will look like this. It becomes twice FNL local times P of Q, P of K. Remember that this P goes as a power of inverse power of Q, like 1 over KQ. So therefore, the other two terms are negligible or much smaller than what I have kept. There are two other terms, but they are, sorry, one other term, but that is small. And of course, there are also corrections over q squared over k squared that I'm neglecting. So this is the leading term in the limit. Okay, so there is this behavior, and this behavior is something very unique in a sense that the nonlinearities that we have in the late universe, the things that Marco was talking about all the time, this bias expansion and all the nonlinear gravitational collapse and evolutional perturbations, that will not produce a feature. Of course, he was talking about delta rho over rho, but that is related to this rate of fluctuation. At the end of the day, everything comes just from adiabatic fluctuation. They will not be able to produce something like that, but at best, in this limit, they produce effects that go as are suppressed compared to this by another factor of q squared. So non-Gaussianity from nonlinear evolution, galaxy formation, whatever messy thing that can happen, all of those are gonna be suppressed by q squared compared to this. And that's why this is something nice to, something promising to look for, because for instance, we can take the bias expansion that Marco wrote, and if there is this kind of primordial non-Gaussianity, you have to add to that bias expansion terms that he wouldn't write. There would be terms that are called non-local, scale dependent, no, non-local, what? Scale dependent bias. So like when he was writing delta galaxy equals B1 times delta plus blah, blah, blah. Inside this B1, there will be a contribution, or this B1 will go to something like B1 times B non-Gaussianity divided by, say, q squared times delta plus blah, blah, blah. So this correction is something that is unique, and this B non-Gaussianity will be proportional to FNL log. So this is something useful too. Something nice that we can look for. And the current constraints on this FNL local, the best constraint comes from Planck. So far we know that FNL local has to be less than 5. Now Marco promises me that he's gonna go all the way to 10 to the minus 10. No. He can get there at some point. Or maybe at 1 order of magnitude, no? All right, so now let's go back to inflation and see what inflation is predicting. Single field inflation. So the claim is that single field inflation, which is what I was talking about, it produces this local non-Gaussianity as a matter of a symmetry. The value of FNL in single field inflation is just determined uniquely and universally by a symmetry argument, and it is very small. It's of order of this Lorol parameters. As a result, if we measure it and we see something different than what that unique symmetry, unique thing that is determined by symmetry, then we know that in we didn't have single field inflation, or at least we didn't have attractor single field inflation. This is called, sometimes it's called single field consistency relation, and it was originally derived in the same paper of Maldacena that I mentioned. Sometimes called Maldacena consistency relation. So I'm gonna go through the derivation very quickly because it's relatively simple to derive it. And then that would be the last thing that I'm saying. So let's go back to this form of the metric that we wrote. I'm including some zeta perturbation. So this zeta long means what? I'm considering a long wavelength perturbation of zeta. So it has already crossed the horizon. Why do I talk about long wavelengths? I'm concerned with this mode zeta q, whose momentum is much less than the other modes that I'm interested in. Very low momentum means very long wavelengths. So what do we want to see? We want to see what is the effect of this long wavelength mode on the other mode. So there is this trick to compute this correlation function in this particular limit. The trick is to consider a universe that some particular realization in which there is one of these long modes. So this zeta L is the same as my zeta Q, so there is a realization of that. The wavelength is of order 1 over Q. And then the trick is to consider some observer or a box here. Some observer who lives in a region whose size is, say, the size of this box is L. There is an observer here. And L is much smaller than 1 over Q. So what this observer sees is just a uniform perturbation in zeta. Doesn't notice that there is a wavelength, there is change. And then inside this box, of course, that observer can measure other short wavelength modes as long as their wavelength is shorter than the size of the box. So for instance, this observer can try to compute the power spectrum of those short wavelength modes. Of course, if I live in a box, then the momenta that I define are quantized by units of order 1 over L. But this is okay. We are talking about momenta much bigger. So there is a hierarchy of scales. So we can talk about, we can put a box in between those. So this is what we are gonna do. We are trying to compute this 2-point function of the short wavelength modes inside this box. Again, I don't write the delta function. I just impose momentum conservation, and you should also remember that this is momentum conservation up to this fact that I'm in a finite box, so momenta are defined in a discrete way. But I want to compute this in a background of this long wavelength perturbation. So this is just a definition. I go from coordinate basis to momentum basis. Zeta of x, zeta 0 in the presence of this long wavelength. Now here is the part that so far I did, this was all general discussion. Now what is the role of single field inflation? The role or the importance or relevance of single field is that remember that we had this argument that in single field inflation, in particular when we are on the slow roll attractor, the long wavelength perturbations are they just correspond to a shift in the time. They are adiabatic perturbations. So the presence of this long wavelength mode actually has no effect on the local physics here. Everything is as if we were in some other unperturbed FRW universe. The only effect that it has is that when I have this beta mode, I can just rescale my coordinates. So just the units that I'm using for co-moving coordinates is a different one. So if I switch to a different coordinate system inside this box, so here if I define x tilde to be e to the zeta L times x, then all the physics that I have in terms of this new coordinates x tilde would be the same as if I did not even have this long wavelength mode. Of course, this is the special feature of this slow roll attractor. And this is the thing that is going to be violated or changed if you have multi-field inflation. Okay, so now what we do is that we just change the variable to this new tilde variable. Oh. In terms of tilde variables, I don't need to write this index zeta. So the whole idea of going to tilde variables is that the only effect of this zeta long is to rescale the coordinates. So therefore this last factor is just an ordinary correlation function. Now if I expand this to linear order, up to linear order in this perturbation zeta, what I find is the following. I will find that, let me keep it here. So I will find 1 minus zeta long times 3 plus k dot grad k, derivative with respect to k, acting on the power spectrum is zeta of k. Of course, there are corrections higher order in zeta that I'm suppressing. Okay, so now we can Okay, so now we can just put it together. What we can do is that now we have related this two-point function in the presence of a long wavelength mode to expand it to linear order in this long wavelength mode, and then the power spectrum of the short wavelength modes. Now, this was a particular realization of the long wavelength mode. Now we want to know the statistics, the three-point correlation function here. So what we can do is to just take this result and correlate it with the long wavelength mode, zeta of q. Then what we pick up is just the correlation of that with this zeta L, which gives us a power spectrum PQ. And as a result, the answer for the three-point function becomes zeta of k minus q over 2, zeta of minus k minus q over 2, zeta of q is given. This is a leading term in this, in similar way as in the equation above, is given by minus PQ PK times d log KQ P of K by d log K. But this derivative is exactly what we how we define the scalar tilt. So therefore, this relation is giving us 1 minus ns times PQ times PK. So now you can compare it, and of course this is in the limit, right, when Q is much less than K. So there are corrections to this result that that are suppressed by powers of Q over K. And notice that this 1 minus ns, it is small. It is suppressed by the Storrod parameter. So it is like 16 epsilon minus twice eta. This is something of order 10 to the minus 2. Okay, so this is what's called single field consistency relation. So single field attractor, single field inflation, we get FNL local, or this particular squeeze limit, to be suppressed first, so uniquely determined by this relation, and then to be very small. And this is probably the most promising way to look for, try to falsify single field inflation. So if we lower this bound and we see local non-Gaussianity bigger than this value, then it will be the end of single field inflation. Now, as I mentioned, if we consider multi-field models, then this argument wouldn't go through, because a long wavelength perturbation or in some other field, it is something that is in principle locally observable, so it can change the physics inside that box. Therefore, in multi-field inflation, when there are other degrees of freedom, you generically expect that this limit will be different. Okay, I think this should stop. And thanks a lot for your attention. I said that if you want to read more about these things, there are my lectures. So there are some other comments about the non-Gaussianity that you can read there, or you can ask me, or whatever. Any questions? Oh, there is also the discussion session, so we can just go to lunch now. Oh, there is a picture.